Good evening, guys.
Good evening, sir.
Only two of you have joined. Let's wait for some time. I think we can begin now. All right. So we have only two guys, two of you. So you have attempted the assignment 3, right?
Sir.
Yeah. Okay. So we will begin solving these questions. The first question is, what will be the total fuel weight fraction for X number of mission phases? So you can see the answer clearly, but do you know the reason why this is the answer?
Yes, sir.
Okay, can you explain?
Sir, this is so because when we will be calculating the weight, entire gross weight of the entire aircraft, sir, we will arrive at the equation that the total fuel consumed during the flight divided by the total gross weight gives the fuel gives the initial weight at that moment, sir.
So can you explain how do we arrive at this expression? You see the expression WF or W naught, and what do we mean by WX?
WX is the weight of the aircraft after the mission, sir.
After the mission.
Yes, sir. And W naught is the initial weight.
Good. So you got the answer right?
Yes, sir.
Yeah. Then I think we will go to now question number 2, because you did it. Most probably everyone else also did it. They're not asking anything. So which of the following is not an application of an airfoil? So to provide thrust for acceleration, definitely yes, because airfoils don't provide thrust. They only bend the flow. Whatever flow is incoming, they change the nature of that flow and nothing else. So answer B is correct. You should know that. Which of the following is not type of an airfoil? Answer is vortex, Anyone has any doubt in this question number 3?
Sir, can you only show what is the diagram of reflex airfoil, sir?
That's a good question. Let me try. Because I've shared this PDF, I can annotate from draw. Yes. So let me try. This is the code line, and a reflexed airfoil has a camber like this, and then in the end goes like this. Okay, so it'll be something like this. So the idea is its camber, first it is positive, then camber decreases, and then again increases. So this is the nature of a reflexed airfoil. Okay. Yeah.
Yes, sir.
Now, can I clear this thing?
Yes, sir.
Eraser. Yes, I can clean this. Let's move to the next question. For the airfoil NACA 0012, what does 12 signifies? It says thickness of the airfoil. So it's a 4-digit airfoil, and there is a predefined nomenclature of that. The number 12 signifies the thickness. So you should know the nomenclature. I'm not describing it here because it's very basic. In fact, I don't even remember. You can look up because it's fundamental and it's always given there. So you should know this answer. A choice of the lower thickness to chord ratio will result in higher critical Mach number. Now, can anyone explain to me what is higher, what is critical Mach number, and
Sir,
how? Go ahead.
Sir, the freestyle at which the speed flowing through the aerofoil reaches to Mach 1 is known as critical Mach number.
Can you repeat again?
Sir, the freestyle at which the speed of the speed on an airfoil reaches Mach 1, sir, is known as critical Mach number.
Good. So for people who did not understand, I will repeat. He's trying to say, how do you pronounce your name?
Sir, Achyut.
Achyut. Okay, because it's a very complicated name. I have not heard this name.
Yes, sir. Everybody seems it to be complicated, sir.
So you're saying that there is a free stream velocity v infinity that is incoming on the airfoil. When the flow encounters the airfoil at this point, flow accelerates on the top surface. I mean, flow is faster, and flow decelerates on the lower surface, or maybe um, goes past this lower surface almost at v infinity. But certainly on the top surface, flow velocity increases. So let's call it some v, and this v is greater than v infinity. Now, what happens is at certain v infinity, which is definitely subsonic, right? At certain subsonic velocity, flow on the wing, not airfoil, flow on the wing, it goes supersonic. And by supersonic, we mean it goes to Mach 1. If you find at one point velocity reaches Mach 1, then the free stream velocity is called as higher critical Mach number. Sorry, the critical Mach number. Okay. Now, why does it say a lower thickness to chord ratio will result in higher critical Mach number? Why is that? Anyone?
Sir, this is so because as the thickness increases, sir, the velocity of the wind which is flowing through the wings, sir, it will easily reach at what is a critical Mach number, sir, due to its thickness. But as it will be thinner, it will the critical Mach number will start delaying, sir, due to due to the thinness of the airfoil and lower drag. So because of this, it will have higher critical Mach number.
All right. I do not disagree with you. So I'll move on from here. Where is the eraser? We go to the next question, which is about computing the stall velocity, and you can clearly see the solution. This formula has appeared so many times that I don't want to feel repeating it. You just substitute these numbers and you get the answer. So let's go ahead. For a cambered airfoil, Cm naught as ACW it's given negative, right? So my question is first, what is Cm naught? Anyone would like to answer?
Yes, sir. It is the value of the CL at 0 lift angle of attack.
Again, can you speak again, Rupinder?
Yes, sir. It is the value of the CL at 0 lift angle of attack.
But can you see the screen, because it's not CL naught, it is Cm naught.
Yes, sir. Yes. Cm naught is also same. It is the value of Cm naught at 0 lift angle of attack.
Cm naught at 0 angle of attack, or Cm value of Cm at 0 angle of attack?
Sir, it is a constant value that remains even if the wing is airplane is not generating any lift wing of this.
Okay. Anyone else would like to answer this question?
Sir, it's the moment coefficient at 0 angle of attack at the aerodynamic center.
Right. Now, since it's negative, so can any one of you derive why is it negative, or it is derived through a long theory and you have to just remember that it is negative, or you are given this number in numericals? Is there any way that we can verify this number is negative? All right, I'll leave this question here. In the next section, I'll try to derive why Cm naught is negative, because I did not bring anything today for this. I'll show you why this number is negative in the next class, because it's important that we understand rather than remember. To trim a flying wing at a positive angle of attack, which of the following arrangement is done? And the answer is reflexed airfoil is used. Now, why?
Because sir, a flying wing doesn't have any tail surfaces to balance the movement created at the AC of the wing. So we need an reflex aerofoil which has a Cm naught value which is positive.
Good. Did everyone understand, or they have doubts, or they want to understand What exactly Rupinder said?
Doubt, sir.
Yeah,
Can you please explain?
definitely. Okay. So where is that annotation? Yes. So what happens is, to trim any flying thing, not just wing, but any flying vehicle, they must satisfy something, which is this equation for the pitching moment. Cm naught plus Cm alpha times alpha. So we are asking that we want to trim at a positive angle of attack, and we need positive angle of attack because we need Cl to be positive, which is Cl naught plus Cl alpha times alpha. So a positive alpha will give us some sufficiently large Cl, and that Cl will directly contribute to the generation of lift on this flying vehicle, not just wing, any vehicle, right? So we need a positive angle of attack for trimming the aircraft. Now, usually for the flying vehicles, uh, the pitching moment equation looks like this. I have shown you this equation earlier also in my sessions, probably one or two, both of the sessions I've shown this equation in some of the other form. So when you trim the aircraft, trimming the aircraft means you make sure at that angle of attack Cm is 0. When you put Cm is equal to 0 and you want to solve for alpha, then you end up with minus Cm naught divided by Cm alpha. Now what happens is, for a stable aircraft or for a stable flying vehicle, Cm alpha is always negative, right? Then there is a negative number. This negative number becomes positive. Now Cm naught has to be positive so that alpha can be greater than 0. So this is the reason why Cm naught has to be positive to satisfy this equation. Now you can ask the question like, where is these contributions coming from? And for that I had I derived actually in the last class, not derived, but I showed the equations for Cm naught, equations for Cm alpha, how they are fundamentally derived from for the wing and for the tail and for the combination of both. So you can go back to those previous videos and see, uh, understand this equation more clearly. But this is the fundamental idea, that you want alpha positive, so Cm naught has to be positive. Okay, then I'll clear this, clear all drawings. Yes. What determines the longitudinal stability of an airplane? They have given the answer, location of the CG with respect to the neutral point. How does it help stability? Anyone would like to answer this question? How do we determine the stability?
Sir, with the help of static margin.
With the help of static margin.
Because sir, static margin is the difference between the neutral point and center of gravity. Gravity, no sir. So it might. So it tries to balances the entire weight of the aircraft, sir.
Right. So it has a neutral point. So anyone wants to answer what neutral point is? Stability increases with the increase in the distance, in this distance. Ron is saying, okay. But before we go to that distance, I want to clarify to everybody that what is neutral point. We have asked this question many times, so you should be able to answer. And I want anyone to speak so that they feel confident. Everyone else feels confident that they know the answer. What is the neutral point?
Sir, may I?
Yeah, yeah.
Sir, it is basically the aerodynamic center of the whole aircraft, we can say. That
Okay,
the change in angle of attack doesn't change the movement around this point. The movement remains constant.
right. So let's say this is the aircraft fuselage center line, and somewhere here is the neutral point. Let's say we are measuring all distances from here, and this is the location of X of NP. Now, at what location with respect to this X and P, or this neutral point, CG should be located?
It should be less than NP.
Less than NP. So CG should be, someone also said in the chat, to the left. So this is to the left. This should be the XCG. Okay. Now, that is a fact, like you read somewhere. Now, how, can anyone help me understand why? What happens when CG is ahead of the neutral point, and what leads you to the conclusion that it is stable?
Sir, if this center of gravity is beyond the neutral point, sir, the stability of the aircraft is highly unstable, sir, because we need aerodynamic center to be more than center of gravity in order to stabilize the aircraft, sir.
Yeah,
If the center of gravity is more than neutral point, that means that the entire weight is at the backwards of an aircraft, sir, which will lead it to stall it upwards, sir.
Okay. I mean, you are not wrong. You are absolutely correct in whatever you said. But my question is more deeper than that. I want to understand, like, you are stating facts, but I want to understand where those facts are coming from, right? So this is your CG, and your weight is acting at this point. So where would the lift force will act? Where would the net lift force will act on this aircraft? AC. Someone is saying AC. So neutral point is the AC of the aircraft. Can I say safely that the entire lift force will act here? And the weight will act here?
Yes, sir.
Okay. So when I take, let's say I increase the angle of attack, okay? Some wind gust came in and it increased the angle of attack. What will happen to the lift? Anyone?
The lift will increase, sir.
Lift will increase. Now, lift will increase, and lift is at the back of the CG. Then let's say there is a delta L lift change because some wind gust hits the aircraft, angle of attack increases. This happens. So this extra lift, what kind of moment it is going to generate about CG? Pitch up, pitch down, what kind of moment it will generate?
Sir, pitch up, sir.
Pitch up. Someone in the chat is saying pitch down moment. Anyone else also wants to answer? What kind of moment it will generate? The extra lift. I'm looking for answers in the chat. Only one answer. Other people wants to join. Please join the answers. Let's see what you understand. Mihir Kulkarni is saying pitch up. All right. So let's talk about it more. So there is this point, and there is this your moment arm. At the end of the moment arm, some force is acting, which is delta L, because L will be cancelled by the weight. So let's say the weight is constant for the duration we are talking about. So some delta L force and this length, call this length some maybe some x, call this length some x. So a moment will be generated about this point with the magnitude of L times x. This magnitude, this L into x moment is trying to rotate this rod, this moment arm counterclockwise, right?
Yes, sir.
Do you agree with me?
Yes, sir.
You agree with me. Now it's trying to rotate the moment arm counterclockwise. So now you replace this moment arm with the entire aircraft. Now what is happening to the entire aircraft? It's experiencing a pitch down moment. No, right? Because if aircraft is flying in this direction and it's experiencing this kind of a moment, so that is a pitch down moment when the lift increased, right? So aircraft is stable in this particular configuration when CG is ahead of the neutral point, and you can give this basic logic, you know, calculation of the moment by introducing a perturbation in the lift. The lift was increased because of certain perturbation. Now, similarly, you can try to understand what happens when the lift increases. Some gust from above the aircraft hits it, then the angle of attack will decrease, lift will decrease, and a restoring moment, a pitch up moment will be created. So, all right.
But sir, it also depends upon the aerofoil we use, sir.
Definitely, it does depend on the airfoil.
If we are using cambered, then this one will be right, sir.
Yeah, we use cambered airfoil in the wing. Definitely, we use that. Okay. So this was your assignment 3. Have you guys submitted assignment 4? I have not registered for this course, so I have no updates. I get updates from other
Yes,
people.
sir. We have submitted 4 assignments till now, and 5th is ongoing.
Okay, so I could have brought the 4th assignment also in this discussion, right?
Yes, sir.
Okay, I forgot that. So, all right, I'll cover 2 assignments in the next session. Okay, so I'll share another screen where we will solve some other questions. Okay.
But the solution of assignment 4 isn't visible till now.
Okay. So they will send it maybe very soon. Yeah. So it's a little long question. 4th assignment is due on 22nd. All right. So by the next session, we will take that. Okay. So this is one assignment from the previous run. I don't know if you have gone through this. Have you guys do you guys also look at the previous run assignments? For example, in the year 2022, when this course was run, there were assignments. So do you guys have access to those assignments also? No?
No, sir, we don't
No,
have.
sir.
Sir, maybe there are some YouTube videos on which the answers of some are given. Not of
Okay.
this year, previous to previous.
Yes, got it. So this is your previous year run assignment 3. So we just solved the assignment 3 from the current run, and now we'll look at what last year people solved. So it's a little longer question, and I want you to bring your notebooks because I will not solve, you will solve. And if you don't answer, we will not move on. We will just stay on this question for long. All right. So this is the question, and I'll read it for you, make you understand. And there are 5-6 questions that we have to solve. There are 5 questions. Yeah. So it's a longer question. It's a good practice question to to get the feel for whatever you have studied so far. Okay, the question says the total weight of the fixed wing aircraft is given like this. So the WTO is total weight, and there are different parts. For example, avionics, subsystems, propulsion systems, they call other weight, structural weight, payload weight, and the fuel weight. Now they've described all of this. What they have given us is that mass fraction of the structure, mass fraction of the subsystems, and power to weight ratio of the aircraft. They have also given us the SFC, brake specific fuel consumption. Have you been introduced to this quantity so far in until assignment 3 or 4? This specific fuel consumption.
Yes, sir.
All of you are aware of this quantity, right? So
Yes, sir.
I think you're ready to use this quantity. And the next quantity is the mass fraction of the propulsion system. So the main idea here is structure has 23% of the total weight. Subsystems have 5%. Propulsion system has 8% of the weight, right? And the maximum L by D for this aircraft is 11 in cruise condition. And we are cruising at 55 meter per second. Okay. In maximum range condition means we are flying at L by D maximum. So, and that speed is 55 meter per second. We are also given the trim CL, and that is 0.3, something called propeller efficiency, that is 0.65. We have been given the maximum range of this aircraft, which is 1000 kilometer. We have a wing area of 6 meters square. All avionics, payloads, and other non-varying weights of the aircraft are 60 kg. So what we know is weights that are not varying. And so what is varying? What is the varying weight of the aircraft? What component has a varying weight?
Fuel.
Good. Fuel has the varying component. So we know the non-varying components. We want to estimate what the varying component of this aircraft. We are given quite lots of information about this aircraft. Now, the first quantity we need to estimate is the value of fuel mass fraction. So answer is given. I think you've seen the answer also, right? No, you have not seen. So I want to show you the answer now. All right. Maybe by mistake I showed you the answers. Nobody took the screenshot probably. So now please calculate the fuel mass fraction. And if you want, I can zoom out a little bit so that you can see the full window of the question. Oh boy. Yeah. So yeah, this is the information and it should be pretty much visible to you. Sit down and bring your notebooks. Keep asking me questions if you have any doubt, and please try to solve this question. First question is fuel mass fraction for this aircraft.
So mass fraction of fuel is asked in the first
Yes,
question.
yes.
Okay.
Okay, so here is some hint for you. I don't know if someone is feeling lost. So one hint is that you can use range formula, Briggs range formula. That range formula has a ratio of initial and the final weight. Okay, before takeoff and after landing. That ratio you can try to compute, and you will get the answer right when you use the right units. So keep in mind you have to use the right units, specifically for the brake specific fuel consumption. The units are not right, so you have to get that unit in proper MKS format, and you could try to use the range formula. Hopefully from there you will get some sense. I will wait for 2 more minutes and then I'll start solving the question. Okay. Anyone got any answer? No? All right. So maybe I'll solve it. So what is usually the range formula? Because I have told you we will use a formula. So do you know any range formula for a propeller driven aircraft?
Sir, for maximum range, we have the CL and CD values,
Uh-huh.
but for that we need the curve slope, drag polar.
Drag polar we need.
Yes.
All right, let's see.
So CL by CD max condition we have for range.
Yes. So we don't need, right?
So we can put that in that Bregwert equation which you are writing.
Exactly. You got it right. All right. So this is the equation. And what are the unknowns in this equation?
Sir, W naught by WF, sir.
Very good. So when W naught by WF is the unknown in the equation, what will be the answer? Range multiplied with C right? And let's call it, because that is a ratio. So we'll come here, beta L by D max. And what else? It'll sit on the
Exponent raised to power exponent.
it'll sit on the exponent. So that is W naught by WF. But is it our answer, or answer is something else?
No, sir, this is fuel fraction, sir.
And what we have asked in the question? What we have?
We need
Yep.
to find the fuel fraction.
Yes, we need the fuel fraction. So is it the fuel fraction?
No, sir. 1 minus this quantity will be the fuel fraction.
Exactly. So the answer of fuel fraction is 1 minus W naught over WF. Okay. I mean, maybe some people might not understand where this came from. Anyone who knows would like to answer?
Sir, which thing, the range formula or this fuel fraction?
This formula.
Sir, we have the sir, I can explain it.
Yeah, go ahead.
Sir, W naught is the takeoff weight, WF is the final weight. So
Okay.
during our flight, only fuel is consumed. And as our range is 1000 kilometer, if we travel 1000 kilometer, our fuel will be totally consumed.
Right.
So the total consumed weight can also be given as total weight minus this consumed weight.
All right. So let me write whatever you have spoken. Achyut might understand it better. So W naught is the total weight. So W naught is made up of what? Weight of the fuel plus the final weight when you land. W final, let's call it. Right? Now you divide it with W naught on both sides, and you need this expression. So W naught divided by W naught becomes 1 is equal to the fuel fraction WF over W naught plus this is fuel fraction, right? And this W final over W naught, it is known to you. This is what you just computed here, right? Inverse of this, right? So you can just take inverse of this and then substitute here, put it on the right side, you have a fuel fraction. Okay. I think it's clear to everyone, right? Is there anyone who did not understand so far what we have discussed? Feel free to ask if you did not understand. I'll repeat it. All right, we can go ahead. So the answer is 0.2. Anyone got the answer 0.2? They're not speaking, so they did not get. All right. So maybe you made some mistake in power. So I'll explain that also. Where is this annotation thing? This annotation thing. There is this brake specific fuel consumption. So the C was 0.6 and it's given in the units of kg divided by kilowatt hour. Did you use it directly or did you convert it into something else?
No, sir, we need to convert it into Newton per watt second.
Very good. So how will we do that?
Sir, into 1000 by 100.
Into 1000 by 100.
Into 3600 seconds.
3600 seconds. Is it correct?
Sir, not the 100 part.
Not the 100 part. So 100 will be removed from here. Now, do you think it is correct?
No, sir, we need to multiply with 9.807 as well.
9.8. Okay, this is 9.8. See, this is kg. So this kg needs to be converted into Newton. So for
Newton.
that, we multiply with 9.8. And this kilowatt hour,
Yes, sir,
it
divided
should
by
be,
1000 as well.
it should be in watt second, right?
Yes, sir.
So
Divided by
kilowatt is
1000.
basically 1000. So this is in watt. Now this 1 hour is basically 3600 seconds. So the overall number is actually this 0.6 multiplied 9.8 divided by 1000 multiplied 3600. Now hopefully you will get a right answer. Okay. Now about kilometers, there was 1000 kilometer in the range. So you have to use basically 1000 multiplied again 1000, because you need this in meters. All right. So we'll clear this and move to the next question. The next question is, the weight of the aircraft in kilogram will be. I think this part is easy now. Can you compute the weight of the aircraft now?
Yes, sir, we have
Yes,
all
sir.
the
We
spread,
can add up the entire weight and we'll get the weight, sir.
But you don't have the entire weight, right? Like, try to see what you know and what you don't know. Then you will understand that you don't have all the things you need. Maybe you have, but just try to see.
Sir, what was the answer for the fuel mass fraction?
0.2.
Okay.
So can we type the answer?
Yes, I will type the answer for you. 0.2 is
For the second question, can we type the answer in the chat box?
if I type the answer, okay, I'll type, but make sure that you let me see what the answer is. Wait, to delete this. 4. The answer is 137.74 kilograms. Notice that the variable, non-variable weight is 60 kg, and you got it 120 kg. You're close, but maybe a little bit off. I don't know why. What did you use, Parth? Can you explain how did you got 120? If your mic is working, you can explain to us. Now you have to do it carefully, because there is a non-variable weight, which is the weight of avionics, other subsystems, and propulsion. Not propulsion. Was propulsion weight given? I don't know. Let me check. No, mass fraction of the propulsion was given. So payload weight is given. Yes. So payload, other, and avionics and subsystems. These weights are known to you to be 60 kg. Right? So I'll put it here. And mass fractions for what? Mass fractions for propulsion, 136.36. That is right answer. Mihir Kulkarni got the right answer. Can you explain, Mihir, how did you get it? You also don't want to explain. Okay, Parth also got the answer. He missed the propulsion mass fraction. All right.
So using the W takeoff formula, W takeoff is equal to the avionics and other weights divided by 1 minus mass fraction of the rest.
Yeah, exactly. So everybody, I think you were introduced to this expression in some of the lectures. I don't recall, but there was an expression like this: W takeoff is equal to W, that is non-varying. So it's summation of all non-varying. I'll just call it NB, non-varying masses, divided by 1 minus mass fractions of all the things that were there. Let's say mass fraction of fuel minus mass fraction of what else? Propulsion, mass fraction of empty weight, right? All of these and structure, empty structure actually. Yeah. So you have to see all the given mass fractions. You have to subtract them, all of them from 1. And for fuel, you have already computed. So you subtract that also, and your known weight is 60 kg. So 60 kg will be divided with 1 minus all the known mass fractions summed here. And then you will get the answer. This is what you did, right? Both of you guys? Yeah, hopefully they did this. Yes, they did this.
Sir, for the
Yeah.
previous question, the expression for fuel mass is exponential of minus RCD by eta into sir.
We missed your voice in the midst of you speaking. So can you repeat it?
Yes, sir. I'll repeat, sir.
It is better that you type in the chat because your voice is breaking. You type in the chat, I'll read it and clarify. And until then, we can go to the third question. I don't want to show you the answers first. And yeah, what is
Sir,
the weight?
for the fuel fraction part, sir, I
Huh.
am getting somewhere missing 1000. 1 10 is about 3 power. I'm missing somewhere because it
Okay.
is coming very low, 0.00022 something.
Okay. So wait a minute.
Also, it isn't coming 0.20. It is coming around 0.228, like
Okay.
that.
So let me clarify the numbers. Okay. I have answers with me. So what is the fuel fraction expression? That is what is asking Achyut. Fuel fraction expression. So this is the weight of the fuel or mass, doesn't matter. And that total weight, the takeoff weight, you can call it. That is the expression for your mass fraction for the fuel. Hopefully it's clear to Achyut. Okay, so I was clarifying for the first question. Again, let me tell you something. So you note down, you guys note down, this propulsion system's efficiency was given 65%. So neta is a given number. L over D is 11. And when you convert the units of C, it turns out to be 1.635 into 10 to the power minus 6. Okay.
Yes, sir. Correct, sir.
Correct. And then you do the manipulation and hopefully we'll get an answer for W not divided by W final. And that would be around 1.2569. And when you invert it, you will get it W final divided by W naught. That would be around 0.7955. And then you subtract it from 1. And then you get it answer is 0.2049. So 0.20 is therefore correct answer. Okay.
Yes, sir.
So W naught over W final was 1.2569 for the first question. Okay. So we will clear all drawings. Yeah. Now the third question is, what is the weight of the power plant in kg? Let me zoom in a little bit. Third question is, what is the weight of the power plant in kg? Try to compute this with the maybe second answer will be used probably. And remember the question is, what is the weight of the power plant? And I'll show you the question again so that you don't miss.
So 10.9 kgs. It is.
10.9 kgs.
Yes, sir.
Let me check. The answer is, you are close, but I'm not sure if it's the correct answer. 10.9088. Hopefully this is the correct answer. 10 or 11. Yeah. Depending upon what your total weight was, right? Because the total weight was around 136 to 139. So probably you are also getting right.
Yes, sir. 136 kg, 136, 136 kg.
Your answer is correct, Rupinder.
Okay,
What you might have done is you taken the 8% of the total weight, right?
Yes, sir. 0.08. Yes.
Yeah, 8% of the total weight. Everybody understood why 8% of the total weight? Because we were given the mass fraction of the propulsion system, and that was 0.08. So all we had to do was multiply 0.08 in the total weight of the aircraft, which is around 136 and 7. Therefore, 11, the answer. We can go to the next question now, because what is the next question? Yeah, the answer is correct, between 10 to 12. What is the peak power required in HP? Peak power means the brake power. We were given a number for brake power, if you remember. We were given this number, brake specific. This is the number, power over weight of the aircraft. So from here, can you compute what will be the power in HP required for the aircraft? Anyone has answered? No? Peak power required in HP will be. So that is the question. And you are given these numbers again. I'll be back in a minute. Did you guys get the answer? I think you can use this number directly. You know, this power divided
Sir,
by
14.23 kilowatts
not in kilowatt, in HP.
in 19 horsepower.
Yeah, that's 19 horsepower. That's the answer. Can you explain to everybody else how did you get the answer?
Sir, we know power to weight ratio of the aircraft. It is per kg. So if we multiply it with the weight of the aircraft, we will get the peak power. And the weight that I've taken is takeoff weight because it is when the aircraft is most heavy and when it is the time when it needed the most of the power to lift off.
Right. So you are absolutely correct. And we have finished all the questions. There were only 5 questions. Oh, yes, there is last question. What will be the trim speed in meter per second? I'll show you the numbers again. And the question is, what is the trim speed? These are the numbers you have. You have your answers also. And the question is, what is the trim speed?
Sir, I'm getting is 11 meter per second, 11.1.
Do you think 11 is a feasible speed for 130, almost 130 kg aircraft?
No, sir.
No, na? So maybe you have to recheck your numbers again. The answer looks not correct. Did you guys get the answer? Okay, I'll explain. Answer to the last question, which is trim speed, and it's almost 34, 35. How do we get this answer? We get this answer like this: twice of weight divided by density, surface area CL. S is given as 6. Rho you can take
Sir,
as.
I've used the same formula, sir.
Did you use 136 times 9.8?
Oh, yes, sir. Now I got it. Yes, sir. Now the problem.
It's the weight of the aircraft, right?
Yes, sir.
Not the mass. So that's why you did not get the correct answer, but now it's clear. All right. We are done with this assignment. Now we will move on to something else for the remaining part of our session. And I'll stop sharing and share again.
Yes, sir, 34.8.
Yeah. My computer is frozen for a moment. I cannot make it full screen. Let me wait for a few seconds.
Sir,
Hopefully. Yeah.
I also want to say, sir, can you please teach us about a bit of lateral stability? Because, sir, the fifth assignment is a lot about stability. This
Okay.
assignment is looking more of a control and stability assignment rather than of a design.
Okay. Like you're talking about the fifth assignment or fourth assignment?
Fifth, sir.
Fifth assignment.
Sir,
So
it is
right now.
asking all about lateral stability, which at least I haven't studied yet.
All right.
Control and stability.
So right now, I may not be able to talk about lateral stability because I have prepared something else. Maybe in the next session, I'll cover that. But if you have questions, for example, because I don't have access to the assignments, what assignments you are seeing, I cannot see because I am not registered for the course. I forgot actually for registration. So I don't have questions in advance, whatever questions you're facing right now. But still, you can send me your questions on my LinkedIn if you want. You have my LinkedIn probably, so you can send me
Yes,
there. Then I may be able to help you there.
sure.
Right now, I have prepared this thing, so we will only talk about this PPT. And you have already seen this in Ghosar's lectures, but I'll still repeat it so that everybody understands it more clearly now. Okay, so when we design the aircraft, the primary goal is the sizing of this aircraft. And the first number that we care about is the total weight. Uh, it may not be the maximum weight, but it certainly is called a design weight. There are situations when aircrafts fly with weight more than what they're designed for. So you can call them overloaded aircraft. So it happens in general for especially for military aircrafts. They usually fly overloaded. So whatever weight we are trying to estimate is usually called the design weight. Okay, it's not the takeoff weight. It's not a maximum weight. It's called design weight, the weight for which the aircraft flies for most of the missions. So this weight is, you already know, is made of the crew weight, payload weight, fuel, and empty weight. Uh, Empty weight here is the structural weight, which consists of propulsion system and other structural parts, for example, wings and avionics. So all of this is usually summed up into one quantity called empty weight. And crew weight we usually know because before the before we receive the requirement of an aircraft, we are told how many people will be flying this, so we know it in advance. Same thing for the payload also. Payload could be the weight of the passengers, it could be cargo. So your aircraft is being designed for a special weight, right? So you know the payload weight also. Now what you don't know is the empty weight and the fuel weight. Both of these weights are unknown to you, right? So what do? We try to express the fuel weight and the empty weight as a as a fraction of the total weight that we are trying to estimate. Now, how does it help us? Because what happens is this fuel fraction, historically it has been found that this empty weight and this fuel weight, they are sort of predictable. We can predict them in advance, depending upon what kind of mission we are flying and what kind of aircraft configuration we are choosing. So what kind of configuration we are choosing guides us to compute the empty weight fraction, and what kind of mission we are going to fly guides us in calculating the fuel fraction in advance. In the previous question that we were solving, we were given these numbers in advance, right? So that was just a algebra exercise, but design is not just an algebra exercise. You have to spend time thinking about your aircraft. Now, with a little bit of manipulations, you can clearly see what manipulations is being done here. This W naught is being taken as outside, and everything else on the right side. So the known weights for you are now the crew weight and the payload weight. These are the two weights that you know, and these are the weight fractions that you have to estimate based on historical data and other aspects that you have chosen to design your aircraft. And we will see through how can someone estimate the fuel fraction in advance, right? And how can they estimate the empty weight fraction in advance when they are designing the aircraft. So let's move ahead. Now, this is the empty weight fraction, and this graph is giving you what kind of aircraft has what kind of empty weight fraction and what is the total weight category of that aircraft. Historically, it has been found that if the total size of the total weight increases, the empty weight fraction goes down. Why is that? Because the weight of the structure, it almost remains constant, right? It almost remains constant to support the extra load. So the extra load is, for example, in the military cargo and the bomber carries missiles or other kind of warheads. So they carry quite a lot of weight. So they're very heavy aircraft, okay? But their empty weight fraction is small, really small, 30%. So that the structure is very optimized and it only has 30% of the total weight. But for a small UAV, it can be as high as 70-80%. 70-80% weight of the small UAV is just the structure, empty structure, right? So this graph comes from historical data. So as a designer, when you sit down and want to design a new aircraft, you have to understand what category of aircraft you are trying to design. Are you building a military cargo bomber? You will pick an empty weight fraction according to that. If you're building a small UAV, you'll pick according to that. If you're building a high altitude UAV or a flying boat, a powered plane, right? So depending upon what kind of aircraft you are trying to build, and you can have an estimation for weight fraction. Someone might ask, like, what if you don't have historical data? Then you have to do all the experiments that these people did. You have to start from the scratch, but that's very hard for the like, you cannot invest that amount of money to get this kind of data. So this data comes from various companies and people over the last 100 years trying to build aircraft. So we have come up with this graph, and when you try to design a new aircraft, you can just directly pick some numbers from here for empty weight fraction. All right. Now, this table is basically extension to the previous graph that I had shown you. How do you compute empty weight fraction is given through this formula. Now you pick a type of aircraft. Let's say you want to build a high altitude UAV, this UAV. All right, let me annotate it more clearly. So let's say you're trying to build this high altitude UAV. You have this number. Oh boy. You have this number A. So Yes, I can shift it. Yeah. So you have this number A. So you use this number A. Then from the previous photograph, you bring the W naught of that aircraft, right? W naught is given on horizontal axis in the previous graph. There was a W naught and there was empty weight fraction. So you bring W naught from the previous graph. The previous graph was like this, right? Notice, I forgot to tell you actually, notice that the slopes of these aircrafts were different for different aircrafts. So for some aircrafts with weight, empty weight fraction goes down rapidly. For the others, it doesn't go down rapidly. It is a small slope. So this slope also varies with the type of the aircraft, and those historical numbers are available in the previous photograph. Now I want to tell you how can you get the exact number, because the previous table, just if you see that the table only gives us an approximate idea of what we are dealing with. Let's say this is a sail plane, for example. Now you don't know exactly what number you're looking at. Let's say sail plane. This is the sail plane, but you don't know what is the number, exact number. It's a range. It's a full range, right? You have a range for the total weight, which is somewhere starts here, it ends here. Similarly, on the y-axis, the weight fraction starts here and it goes there. So this entire domain is on y-axis, and this entire domain on the x-axis. This belongs to the sail plane. All right. So now you can do iterations in these range. So when you try to build an iterative approach to find out a particular total takeoff weight for your aircraft, then you should look into this range only. If your answer is coming out of this range, probably your answer is wrong. Okay. So let me go to the next slide again. Yeah. So what I was trying to tell you is, oh boy. Clear all drawings. Yeah. What I was trying to tell you is how to compute this fraction exactly from this table. The previous graph guides you to choose a total weight, and this graph, this table guides you to compute exact empty fraction for the kind of aircraft you're trying to build. Let's say you're trying to build some high altitude UAV. So you're gonna pick a 2.75 from here in this table, which is 2.75. Now you go back and find out the proper W naught, the range of the W naught, because W naught is not a fixed number. You cannot pick it directly. So there is a range. So you have to look at the entire range. And in that range, you have to look at all possible empty weight fractions. All right. One W naught that you pick from that previous photo is not going to help you. You have to look for all possible weight fractions. There is a range of weight, right? So you should look for those weights. Then you take the power of this W naught as some number C. That some number C is given here. So for this number is minus 0.18. So you take this number minus 0.18 and put it here. Now, the question is, if your aircraft has a swept wing. So for the swept wing, you include a factor KVS. The swept wing is heavier actually. They have a heavier empty weight fraction. So this 4% higher, 1.014 is a factor that you multiply when there is a sweep in the wing of your aircraft. So someone might ask you a question. Which kind of aircraft is heavy? Swept wing or fixed sweep wing? So the answer should be swept wing. Swept wings aircraft are more heavy, and almost by 4% historically. So yeah. Now understand, this table is not exact, but this table guides you for your initial calculations when you are designing something. So it helps you, right? Then let's go back to the first slide just to understand what we have computed so far. Now, when we are on the mission of computing total weight. This is total weight of the aircraft. We were able to understand empty weight fraction, structural or other weights. This empty weight fraction, we were able to understand it based on historical data from different aircrafts that different companies and people have built over the years. But now the only unknown for us is the fuel fraction. So now let's go ahead and try to find out if we can compute the fuel fraction. Now, fuel fraction is dependent upon directly dependent upon what kind of mission you're going to fly. So this is case one. In this case one, just look at this photo. Okay, I want to ask any one of you, explain to me what is happening in this picture. What is aircraft doing here from 0 to 6? I mean, you can read it, but give me try to give me a sense of what kind of aircraft is it.
Sir, a simple passenger aircraft,
A normal jet
civil
transport
aircraft.
aircraft.
Yeah. So it warms up at 0, goes to 1 by taxiing, takeoffs, climbs until 2, then it cruises from 2 to 3, then it descends to 4, then there is a loiter 4 to 5. Anyone has any idea why there is a loiter in almost every, not almost, on exactly every mission? There is a loiter 4 to 5. Why is that?
Sir, this is because whenever the flight will be landing, sir, it need not be necessary that the runway will be cleared, sir.
Very good answer. How old are you, Achyut?
Sir, I am right now 17, sir.
You are a very smart boy. You will do great things, man. So his answer is absolutely correct. Runway might not be free. Other situations could be like it's very foggy, it's rainy, right? Takeoff is not sorry, your runway is not available for landing. You have to account for loitering in every aircraft. Once you are in the air, you should have 30-40 minutes of extra fuel. Whatever you do, whatever your mission is, finish your mission, and apart from that, you should have a 30-40 minutes of extra fuel for loitering. So every mission will consider that extra fuel, right? There are regulations from different agencies that certify aircrafts. All right. So this was a simple passenger cruise aircraft. Now this one is commercial transport aircraft. So it's slightly different. Anyone wants to explain to me what is the difference?
Sir, the difference between this simple cruise and commercial transport aircraft is that in simple cruise, the passenger aircraft takes from one airport and it lands at another airport.
Right.
But whereas for commercial transport, like military ones, they climb, they cruise, again they loiter, they land. There they unload the items, whatever is loaded in the aircraft, and again they fly back to their base, or they'll fly back to nearest base.
Right, you're almost right. Also consider that this is only an attempt to land, right? So what happens with commercial transport aircrafts is they factor in wherever they are going. Okay, wherever they are supposed to land. Let's say you are coming from New York to New Delhi. So you have to consider that you should be able to land in Chandigarh or Lucknow also. You are on Delhi, but Delhi, let's say, doesn't have accessibility for the runway. You don't have accessibility for hundreds of reasons. Okay, so you should be able to divert your plane to maybe Chandigarh or maybe to Lucknow or to the other nearest airport, right? So that you have to factor in when you are flying, let's say for 10 hours or something. So you have to factor in that you should be able to go to the nearest airport. So that is factored in here. So you are diverted to the nearest airport. For commercial transports, this is a requirement. When they put the fuel into the aircraft, they take this calculation into account, how much fuel they are supposed to fill. What kind of aircraft is this? The third one.
Sir, bomber aircraft.
Yeah, it's a bomber. It goes, drops the bomb, comes back, right? So why am I showing you all of these pictures? These pictures I'm showing you because you need to compute how much fuel is consumed from 2 to 3, how much fuel is consumed from 1 to 2, from 0 to 1, the ratios for all of these. So you compute ratios for all mission segments. So when you design an aircraft, you have to clearly decide what your aircraft is supposed to do, how many mission segments you have, right? And factor in all other possibilities like loitering and diverting. Consider all of them and then factor in the total fuel, right? So now, what is this aircraft? The last one.
Fighter jet, sir.
Yeah, it's a fighter, air superiority. It has to do combat also. So consider how much fuel it is going to consume in the combat, right? So yeah, now you get the idea. When you build an aircraft, you clearly define on paper what your aircraft is supposed to do, how many mission segments it has to have, and for certification purposes, how much it should loiter, should it be able to divert, right? Should it be able to combat, depending upon if it's a fighter or a commercial aircraft, right? So yeah, erase all ink on slide. Yep. Now when we compute the fuel fraction, so all of this calculation is done for a particular type of aircraft, and you compute this fuel fraction. But the answer is not so straightforward, right? I'll show you how. Yeah. So notice the goal is to compute this WF by W naught, but I told the answer is not directly simple. For these calculations, you have to spend a lot of time and thinking. Now let's look at warm up and takeoff. So warm up and takeoff, from warming up to the takeoff, the only 3% of the fuel is consumed. In climb historically, so this is coming from historical data, so you don't compute separate calculations for these things. So warm up and takeoff, climbing and landing, this is kind of historical data. It's coming from what different aircrafts are consuming, right? So these numbers you can directly pick from here for these 3 missions. But let's say for range, one aircraft is supposed to fly 500 kilometers, the other is supposed to fly 1000 kilometers. So the fuel fraction is definitely going to change, right? So you have to compute this ratio. This ratio you have to you're supposed to compute depending upon what range is specified to you. So you know the range segment, the cruise segment fuel fraction. So you compute, this is the fuel fraction, Wi and Wi minus 1. So it's the previous and it's the current location. Let's say you started cruising at I minus 1 and you are currently at I. So Wi over Wi minus 1 is the weight fraction. And this is endurance. So endurance accounts for what? What kind of?
Sir, it means that the time duration in which the plane was in cruise.
In cruise, I can tell the range. Cruise is always specified mostly in terms of range. Let's say 1000 kilometers you want to fly. But endurance specifies what? What kind of mission endurance specifies?
Least fuel consumption and least power use.
No. The question is very different. The question is, let me go back to the previous slide. Does endurance accounts for climb or descent or land, cruise, loiter?
Loiter, sir, loiter.
Loiter. So you should be able to loiter for certain minutes, let's say 30-40 minutes. So for that you need endurance. So when you factor in loiter, you do calculations, the weight calculations for endurance. You take in some endurance and then compute the weight fraction for the loiter. All right. So now we have not included the combat and weight drop and all of those things because they are complicated, and I mean, you understand the concept, right? So when you want to design a fighter, you will find books on that, so you can read that. But you get the idea how things proceed when we want to compute the takeoff weight of the aircraft. So,
sir, I'm having a doubt, sir.
Yeah.
Sir, the previous slide which you showed, that was range and endurance for jet engine. No, sir.
Absolutely.
So similarly, can you just show a slide for propeller-driven engine?
I did not bring, but yeah, you're right. We can have a range for propeller-driven aircraft also. So, in one question, the last question that we were doing, this was the expression for that. Log W naught divided by W final, something like that. So you can use this expression, and you will have a propeller efficiency and SFC in terms of the power that your engine is producing, right? The piston engine that you have on board the aircraft. So this is the range formula for your propeller driven aircraft. You can have that.
No, sir. I want a formula for fuel fraction, sir.
I mean, all you have to do is change this number. You understand?
Yes, sir.
So when you compute for a propeller driven aircraft, you will not use this formula. Definitely you will use the formula for propeller driven aircraft. But what I'm trying to give you is the concept. Okay. What you do is you break your mission into segments. Now you choose the configuration, the type of the aircraft. Depending upon the type, you use the formula. Now I'm showing you these calculations for a jet driven aircraft. Okay.
Yes, sir.
Yeah. So now, when you compute the range for different aircrafts, you are required something called specific fuel consumption. Now, this is the fuel consumption numbers that you can pick directly for what kind of power plant you have on board. Because see, when you compute range, you need C, but you don't know C. Maybe you have not really you don't know the exact engine that you are going to use, but you know the type of the engine you're going to use. Maybe you know in your mind from conceptual design that, yeah, we are going to use a propeller driven aircraft. So you will replace this formula from the previous formula that I described. Or if you have a jet driven, what kind of engine you have in jet driven? Let's say you have a high bypass ratio turbofan engine. So these are the numbers for that. You have turboprop or piston prop, afterburning turbo. So different kind of power plants you have, and based on those power plants, and based on your flying Mach number or velocity that you are being specified, because always you are specified Vmax of the aircraft. So you know the V Mach number corresponding to that, because you know the atmospheric conditions in which you will fly and what kind of engine you have. So you choose your engine, your Mach number during the conceptual design stage, right? The Vmax is given to you as a requirement. So you have a number, good estimate for the specific fuel consumption. Then you are ready to compute this, but still you don't have one number. What number we don't have in this range and endurance formula?
By D.
Very good.
L by D.
We don't have L by D. It's a complicated number, right? L by D max. Usually we prefer L by D max. So we want to fly the aircraft at L by D max usually. So we need the L by D max. So how do we get it? You know, if during the whole let's say cruise flight, you know the total lift on the aircraft from the total weight, because you used a total weight approximation earlier also here when you computed the empty weight fraction. So you had an estimate for total weight. So based on that total weight, you can compute a approximate idea. You have an approximate idea about the amount of lift that you will be generating while flying this machine, but you don't have a very fair idea about what kind of drag it will experience, right? So drag is dependent upon two things. Drag has two sources. It's induced drag, it's a parasite drag. I want from you people to understand what is the difference between induced drag and parasite drag.
Sir, induces from lift, but the parasite drag is due to skin friction interference drag and the form drag.
Exactly. So parasite has this skin friction is a major component of parasite drag. And since you know the lift, you can estimate the induced drag, but you cannot estimate the parasite drag, right? Very precisely until you know the surface area of the entire vehicle, which you have not already designed. So you don't know actually what parasite drag your vehicle is experiencing. But for that also we have got some tricks in the book. So these are the numbers again for the SFC that we have already seen, and for some something for propeller driven engines also, SFC for propeller driven engines also. Now we were looking for prediction of the drag, right? So it turns out that drag depends on aspect ratio, but not just the aspect ratio. It depends upon the weighted aspect ratio. A weighted aspect ratio is something different from aspect ratio, and I'll explain how. What is aspect ratio? Aspect ratio is usually defined as b square divided by s. So b is your span, your span of the aircraft, b. Okay. Now, what is this s? This is your wing area.
Wing area.
This is your wing area, right? So you define this aspect ratio, but parasite drag comes from these parts also, right? From the nacelles.
Yes, sir.
Of parasite drag is coming from here also, right? So aspect ratio is not a good prediction of the total drag that aircraft is experiencing. For that, we define something called weighted aspect ratio. This is called weighted aspect ratio. So how do we define that? We define as weighted aspect ratio with the same formula, but we say b square divided by s weighted. So weighted area means all the area that is exposed to the air. Okay, all the aircraft area that is exposed to the air, not just the wings. That is weighted aspect ratio. Now, a weighted aspect ratio for these two different aircrafts is almost same, 1.2 and 1.4. You see there, this is delta wing and this is a simple swept wing. They are two different aircrafts, right? Do they look similar at all? Do you guys think these two aircrafts are similar, or do you find they are different?
Sir, they are different, sir, entirely different.
They are absolutely different aircrafts. But you will find out that they have a similar weighted aspect ratio, and therefore they have a similar L by D ratio also. It's very non-intuitive idea, but for these two aircrafts, L by D is same. L by D max is same for these two aircraft. So what you really do is, when you are looking for L by D and value of L by D for your design, you don't look for the aspect ratio, you look for the weighted aspect ratio. Now for that, we also have some form of historical data, right? So this is weighted aspect ratio, and this is L by D max for that particular kind of aircraft. This is historical data. So you can pick, now let's say fixed gear prop aircraft, military jets, civil jets. So you can pick a approximate number from these, right? So this table also helps you in picking up a L by D max and weighted aspect ratio for your aircraft, depending upon this table. You see all the previously built aircraft and try to understand if your aircraft configuration is similar. So all you have to do is look for the configuration. Now, are you building something like a B-49 bomber or something like Boeing 747, right? So if you know the nature or the configuration from your conceptual design, you can pick a fairly good aspect, L by D max for your aircraft, right? And now, once you are able to compute all the, let's say, what I want to tell you is, once you are able to compute all the ratios for these missions, in this slide I want to tell, let's look at it. We were saying something like Wi minus over W, sorry, Wi minus W divided by W, yeah, something like that. So you will have W naught divided by W1, W2 divided by W3, W4 divided by W5, something like that, right? So you multiply all of these ratios and you will find out that what is the ratio of W0 over this W maybe 6, the final. And once you know this number, again, you can compute the fuel fraction as we did in one question. So that was, you just subtract it from the one, your W0 over W final, or maybe the opposite, W final or W0. And this is your fuel fraction. So that formula I have shown at the end. Now, this is WX mission segment. So from beginning to the end, X is the number of the mission segments. So you can 7, let's say 7. So X is 7, W7 by W0. You know this number, you subtract it from 1, and then you get the fuel fraction. But where is this number coming from? 6%. So this is unusable fuel. You cannot use it because maybe you cannot pump it. Wings are designed such that there is some fraction of the fuel that you cannot pump, right? Cannot use in the engines. So usually this number is around 6%. So you multiply the fuel fraction by 1.06 instead of 1. So you add this, you factor in basically the extra fuel that you are carrying. So now this entire design procedure is listed here. Design objectives and sizing mission. You design a sketch, right? You choose L by D max, L by D cruise. You find out the fuel fraction. You guess some W0, and you find out empty fractions, and you do this calculation over and over. And ultimately, you will converge on a design that is optimal for your mission. So I have given you basically the outline of how the design procedure moves. So yeah, that's all for today from my side. And yeah, I'll stop sharing now. All right, guys. And we have just 10 minutes. So if you have any other questions, we can answer.
Sir, please explain us the lateral stability in the next class.
Yeah, definitely. I'll do that. I'll prepare one slide on lateral stability because I already explained this longitudinal, right?
Yes, sir.
So in the next lecture, I'll take this lateral stability. Also, should I talk about control also? I mean, the control surfaces. Yeah, we should talk about control also, because at one point you will have to design control surfaces also. Yes, so we can talk about that also. For the next session also, we will solve some previous run questions. We will solve assignments from the current run, and then we will look at the extra topics. Just like this session, we had taken the design part. I know that this part was taught to you in the class also, right?
Yes, sir.
Yes, sir.
Yeah, so I just reiterated it because I found it interesting. So
Yes, sir. The
there's a
graph
book
and
called
the
Raymer.
historical data wasn't shown on the lecture.
Yes. So there is one professor, Raymer. So he has written a very beautiful book on design, aircraft design.
Yes, sir. Yes,
So
sir. Book. I'm reading it. Correct.
yeah, because I was supposed to teach you. So for the first time, I read this book and I found it very interesting. So all of these graphs that I've shown you are from Raymer, chapter 3. And whatever I have covered in this session is the entire chapter 3. We've covered the entire chapter. And what I'm gonna do with these sessions is I'll pick one chapter every session. So apart from your assignments, I'll teach you something from that book. So if you don't understand, you can go and directly understand from the book also. You can talk to me, and then you will have a very good idea about aircraft design process.
Sir?
Yeah.
Sir, can you just once again show the reflexive aerofoil, sir?
Yeah, I'll try to. One note. this one out. So what happens for the reflexed airfoil is usually, yeah, first we should look at the usual airfoils, what happens to their camber. So let's say this is the chord line, and for the usual cambered airfoils, this is what happens, something like this, right? Now if you draw the camber line, it looks like this. So camber initially increases, right? It's positive in the beginning, then it flattens, and then it starts to decrease, and it just goes to zero. Now what happens in the reflexed airfoil, this is your camber line, and let me draw directly the camber line. So it drops and then it starts to increase again. So this is different from the usual airfoils, right? I'm showing it exaggerated photograph so that you get a sense of what kind of airfoil is this. So what happens to this airfoil is that at the back, the camber starts to increase. So it goes close to zero and then it starts to increase. The camber is basically the distance between the chord line and the camber line. So that's what happens in the reflexed airfoil. Now you got the idea?
Yes, sir.
Yeah. Now here is some assignment for you. You read about the reflexed airfoil and what happens when the camber at the back starts to increase. What are the effects on the aerodynamic behavior of this reflex airfoil? So I will ask you, this question is specifically for you. So you will have to speak for 5 minutes. You might share your screen also.
Yes,
So
sir.
present to all of us what reflexed airfoil does, okay, how it behaves aerodynamically.
Okay, sir.
Yeah. So you will also benefit, everybody also will benefit.
Thank you, sir.
Yeah.
Thank you, sir.
Yeah, thank you. I'll just wait for 3 more minutes and then I'll end this session because I'm supposed to be here for at least 2 hours.